So, good evening. So, today I'm going to present on the topic on the project that we had taken as part of our computational physics course in semester 3. Actually, along with me, there was two other students also who worked on it. And unfortunately, one of them could not make into the meet today. Else, we would have been two giving this in this webinar. So, let me get started without any delays. So, what is the need of Hohmann transfer? So, you can see here clearly that there is a cat, let's say it's a Schrodinger cat, and it is inside the box solving equations. So, the main aim of it is to come out of the box and destroy the whole world. So, we need to escape from this planet, right? We need to go to other universe. So, that's the need of Hohmann transfer. Anyways, jokes apart, let me get into the topic now. So what is the need mainly? So if you look at interplanetary missions play a very important role. You see NASA is mainly working on it, made its Perseverance mission which took to Mars in 2020, or its Viking mission, or let it be even you know even ISRO has worked on Chandrayaan 1 and Chandrayaan 2 and even Mangalyaan and many others, right? So interplanetary mission plays a very important role because we need to know as to what's happening in the planet. The research in that field is very demanding because there is a search for another life, if life is possible in another planet, or if there is water in another planet, or what is its composition and all, right? So if you look at the cost of Mars's 2020 Perseverance mission, it was around roughly around 2.75 billion US dollars. In that, though the rover costed itself around 2.2 billion dollars, so the another $500 million was spent on the vehicle charge. That is the transfer vehicle charges or the other cost, whatever. But when you look at the Chandrayaan 1 cost, it was roughly around 380 crore Indian rupees, and then Chandrayaan 2 was around 960 crore rupees. So what you see is we are spending a huge amount of money, and that too it's a taxpayers' money. So always what we look into is we need to minimize the cost. So one of them which helps in minimizing cost, and there are is these transfer techniques called as, there are many transfer techniques which I'll come in the next upcoming slides. So that is one of the main necessity here. Okay. So now if we let me go to the next slide. Interplanetary missions are really very costly. So we need a huge amount of fuel to provide the required energy, right? So Hohmann transfer is one of the such process that helps us in simplifying the process and helps in doing it in a fuel efficient way. So most of you know that if in our childhood we would have at least played this game called Kerbal Space Program, right? There we do not consider any of these transfer. We directly do the direct transfer of plan of of the spacecrafts initially. Before we know how to use it, this used to be our plan, right? We will directly shoot into that destination. So I have divided my talk into four different parts, starting with introduction, then followed by computation, and then I'll be doing the analysis, and then finally with the conclusion. Right? So what is Hohmann transfer? A Hohmann transfer is an orbital maneuver that transfers a spacecraft from one orbit to another orbit. Fine. So let's look at the history of it. The first mention of Hohmann transfer goes to in 1925, where Walter Hohmann wrote about this in his book. In this book, which is written in German, which is really difficult for me to pronounce, though. So the meaning of this book is the attainability of celestial bodies. So the book title itself says it is a way to reach the heavenly bodies or celestial bodies, right? So let us see who was this Walter Hohmann. So Walter Hohmann actually was born in 1880. He was a German scientist, but the reality is that he was actually trained civil engineer. But since his childhood, he was very much interested into German science fiction. He was very much interested in this book called The Two Planets, written by Kurt Lasowitz. So this was the book which actually motivated him to work on astrodynamics, mainly in the field of orbital mechanics. So in 1912, when he was reading this book on astronomy, there was something that sparkled him about the space flight. So he started working on this technique. So I said you before only, right, that there are many different type of transfer techniques available. So one among them is bielliptic transfer and Hohmann transfer. There are many others like low thrust transfers and others. So mainly, what is this bielliptical transfer orbit, right? So you can see this is sun, and this is where we are starting. So let us say this blue color one. I think you can see my cursor. So the blue orbit is my origin orbit. That is, I'm starting from here, and I have to reach this orbit which is in red color. Okay, that is what I marked as 3. So what I do in bielliptic transfer is when my spacecraft is here, I'm now talking about after the rocket has been launched and the spacecraft has been successfully put in the orbit. I'm at this position now. Okay, so I'm launching. It is orbiting around here, and when it comes somewhere here, I give an extra velocity here such that it will take this elliptical orbit and it reaches this orbit. Okay, let me call this orbit as the one in orange in dotted line as target orbit 2. Fine. Once I reach this target orbit, right, I give one more velocity in such a way that I'll just allow my spacecraft to come till here, and once when it comes here, I'll give one more velocity in such a way that it will go in the my destination orbit, so this red orbit. Okay, so here we are involving two elliptical transfer, and there's three places where I'm giving velocity injection or impulse. Okay, that is one at point 1, one at point 2, and point 3. So bielliptical transfer has a three impulse. So this is what you need to keep in mind till the end of the talk. While the same thing in Hohmann, let's say Sun is somewhere here, and this is my origin planet, and I have successfully installed my spacecraft somewhere in the orbit. So what I do now is my spacecraft will be orbiting somewhere like this, and when it comes to this point, right, I will give an extra impulse of delta v. So because of this extra impulse, right, it will try to match. It will go in an elliptical orbit, and once when it reaches this point, right, what I'll do, I'll give one more velocity in such a way that it will go in my destination orbit. That is this red color orbit. So mainly here there is only one ellipse involved and there are only two impulse involved while bielliptical was involving three. So you might think that okay, bielliptical is having three impulse, that means it should be consuming more energy. But no, this is not the case. So we'll look into it in the next slide. So here I put some of the data regarding how much delta V is needed. Let's say if we are starting from some orbit at some height from the Earth, and I'll neglect the height of the orbit where I'm revolving and compared to the radius of the Earth. So if I want to go to Sun directly using Hohmann transfer, the impulse I need to give, that is this impulse delta V, I need to give is around 29.8 kilometers per second. While for Mercury it is 7.5. While for Venus it is 2.5. This is in kilometers per second. Okay, and while for Mars it is around 2.9 and Jupiter around 8.8, Saturn 10.3, Uranus 11.3, then Neptune 11.7, followed by Pluto at 11.8. And if you want to go to infinity, then it is 12.3. So you can clearly see that it is somewhere about to converge to this point, right? So this is one observation you have made. So now I said that, okay, why do we have two transfers when Hohmann has only two impulse, so it should be lesser, right? No, I'll just divide it into two cases. The bielliptic transfer consists of a two half elliptic orbits, and they require one extra burn than Hohmann transfer, right? But bielliptic transfer requires more delta V than Hohmann when the ratio of the radius of destination planet to the ratio of origin planet is less than 11.94. This ratio is of the radius. That is, let's say this is Sun, right? So let's say this is our origin planet. So the distance from Sun is our origin here. So this distance is our origin and this is my destination, right? So this distance to the destination orbit is our destination from the Sun, because mainly we are considering Sun's gravitation, so we are taking distance from there only. So this is clear, right? When the ratio is less than 11.94, yes, Hohmann is more efficient for us and we will spend less energy to this. But when the ratio is greater than 11.94, right, then Hohmann turns out to be a villain for us. It will take more energy than bielliptic. So bielliptic will consume less energy in this case. Fine. So I think now we are clear as to why we prefer both the transfers, right? Now this is the curve we plotted. You can see that in y-axis we have change in velocity in kilometers per second, and then in x-axis we have distance, that is r in astronomical units. Fine. So you can clearly see that this is the curve for Hohmann. Then you can clearly see that for somewhere between 0 to 11.94, this is that point 11.94. You can see that let's say somewhere this is around 2, right? Let's say this is around 4 for 4 astronomical units. Then you can see that this is around 3.56, right? This is around 3.56 kilometers per second. But if you were about to do the bielliptic transfer, then this is around 4.56. That is, you are spending up more energy here in bielliptic. Whereas post 11.94, you can see that all the bielliptic curves are below the Hohmann curve, right? So Hohmann curve is more efficient here in this case. Fine. So as I said in what we used to do in our childhood in Kerbal Space Program is that we used to do a direct shoot. That is, we used to just put our rocket from one orbit directly by continuously, by continuously burning the fuel. We used to go directly, right? Let's say this is the sun, and I'm orbiting somewhere around this orbit, fine. And this is my the destination planet where I want to reach. By the time I go from here to here, I'll consider my planet also will reach here, fine. So what if I will just continuously burn my fuel and then go there, right? Of course, you can do that. There is no harm in doing so. But the thing is, again, you are spending more energy. So there is more demand for fuel, and there is more expenditure of amount, right? So the techniques which we are using, Hohmann and bi-elliptic transfer, demands patience. That is, you would have seen even there are, like, these missions take up to 2 years, 3 years to reach the destination planets, right? Even though their speed is in range of thousands of kilometer per hour, still why do we take more time? This is because we are orbiting around in a elliptical orbit or a circular orbit in such a way that we'll minimize the energy consumption. So this is one reason. So the shortest path is always a straight line, and to reach there, we need to continuously fire the engines. But Hohmann just takes firing at two different locations for just a short interval of time, right? And then we are making use of sun's gravitational force to reach the planet, hence which is making us to consume less energy. Gravitational force is a central force which will always pull you towards the center, right? So this will make you to go in an elliptical or a circular orbit, right? So we are making use of this technique, and hence we are spending less energy. So these are some of the data we have taken for the simulation. So you can see there are around 9 planets. Though Pluto is not a planet, let's just consider. We'll not do partiality with Pluto. Mercury is at around orbital radius of 0.387 astronomical unit. So right, it is always measured from Sun. We assume Sun to be at one of the focus, and then we measure the distance, right? So Mercury is at 0.387 astronomical units, and then in another column we have time period. That is, how much time does it take to rotate around Sun? This is around 0.24 years. Why this data is important, I'll let you know in the upcoming slides. And the eccentricity of the Mercury's orbit is around 0.205, and mass of the times 10 power minus 6 times 0.166 times the solar mass. Though you can see that I have mentioned M Sun, in most of the books solar mass is represented as M and then a dot, right? So similarly, I have all the data taken for all the planets, and this is data we have taken from NASA's data fact sheet, right? So now let me explain you how does this work. So I'll just go to a whiteboard. How does Hohmann transfer exactly work? So you can clearly see that this is my origin planet. Let's say this is Earth, and then I have placed my because let's say this is okay. Let me just change the color. So we have Earth somewhere here, and then what I do first, we launch the rocket and we put it in an orbit, right? We put the satellite in this orbit. So this is revolving around this orbit. And then I just assume that this height is very, very negligible when compared to the radius of the Earth. Fine. So I'll say that my satellite is somewhere here. My spacecraft is somewhere here initially. Fine. And this is my destination planet. Okay. I'll write it as, I'll just mark it by a star. So this is my destination planet. And I'll say that the angle made by my origin planet, Sun, and the destination planet is phi. I'll tell you why this angle is important. This is called as eccentric anomaly. Right? So eccentric anomaly is the angle needed for a successful Hohmann transfer. Right? Even when the launch window for Earth for a spacecraft from Earth to Mars is once in every 26 months. That is the suitable time when you can launch your spacecraft. Okay. So I'll say this angle is some angle phi, and when this angle is exactly phi, I'll just give this velocity delta v1. Right? So when I give this delta v1, this will start moving in an elliptical orbit, and when this coincides with my destination planet's orbit, that this orbit will coincide with this in destination orbit for sure. And when it does, I'll give one more velocity in this direction. This is delta v2. Fine. This is delta V1. And I will this point I call it as perigee because this is near to Earth. And when I reach this point, I'll call it as apogee. Fine. So I hope, and the distance between origin planet and sun is RO or R origin, and distance between sun and the destination planet is RD or R destination. Fine. I'll derive it now. So I hope this diagram is clear for everyone. And now some I'll you know that to achieve a complete perfection is difficult in science, right? So there are always some assumptions taken. So what we assume is I assume is all planets are in the same plane. Fine. Then I'll assume gravitational effect of sun is only dominant in the entire solar system. And the one more thing that we assumption that we have taken in our code is that the position of all planets in the solar system is randomly fixed, and we but except for the planets where we the origin and the destination planet, we are fixing the eccentric anomaly. That is, if I have to transfer from Earth to Mars, the position of Jupiter, Saturn, Uranus and Neptune are random. Okay, and then position of Earth and Mars are fixed exactly at the eccentric anomaly. Fine. And other some of the idealities that we are talking about is, that I'm assuming here that all planets are in a same plane, right? But that is coplanar. But you know that again, Pluto is not in the plane, and that is why it has been taken out as a planet, right? And then again, Mercury has a precision, that is, it is around changing around 42 arc second every century. So all these consideration we have just eliminated. And also we are considering gravitational effect of sun is dominant throughout the system, entire solar system. That is, let's say if you are transferring from Earth to Mars and Earth to Jupiter, let's say, and when you have to pass through an asteroid belt, or you're passing through Mars, then you'll have the gravitational effect due to these planets or these asteroids also, right? But we are neglecting that because that is very small when compared to gravitational effect of sun. Okay, so let me start with the derivation. So you are now clear with the nomenclature of the terminologies that we'll be using. So when the spacecraft is launched from Earth, it is orbiting around Earth and also orbiting around Sun, right? It is orbiting around Sun in a separate orbit. So I'll call that orbital velocity as V origin, and I'm giving an additional impulse of delta V1. So let me go. So this when I'm going around this orbit, my orbital velocity is V origin. And now I'm giving a extra velocity here, that is delta V1. And this velocity I'll call here as V perigee. So this V perigee is now the sum of V origin plus delta V1, right? So similarly, when the spacecraft reaches the apogee point, it's having some velocity V apogee. And I'm giving an additional impulse of delta V2 to match the orbital velocity of the destination planet around the sun. That is V destination. That is V destination is my orbital velocity of the destination planet. Okay, it is so that will turn out for me to be V apogee plus delta V2 is equal to V destination. Fine. Remember these two equations. We'll be using it at the last. Fine. And in this entire system, angular momentum is conserved. This is mainly because net torque is 0. So if angular momentum is conserved, I can say L initial is equal to L final, right? And then if angular momentum is given by mvr, so I can say m spacecraft into V perigee into R origin should be equal to m spacecraft into V apogee into R destination, because my initial point is um, in the perigee and my final point is apogee, right? So I'm conserving angular momentum there. So you can clearly cancel m spacecraft on both the sides, and V perigee will be now equal to V apogee into R destination by R origin. Again, remember this equation. This is one of the important equation which we'll be substituting in the upcoming equations. So when momentum is conserved, even energy is conserved. That is, my Hamiltonian is conserved. That the total energy conservation in the sense, I mean the total energy is conserved. That means in a more deeper term, Hamiltonian is conserved. So my energy initial should be equal to final energy, right? So my initial energy is the kinetic energy at perigee minus the potential energy is equal to E initial, right? This is my E initial, while my final is again kinetic energy plus potential energy. Potential energy is always negative. So that is why this negative sign is popping up. So I hope this is clear. Now, when I equate both, again, you can see that M spacecraft can be cancelled on both the sides. So when I cancel it, it will be half times v square perigee minus gm sun by r origin is equal to half time v square apogee minus gm sun by r destination, right? So now I'll rearrange these terms. That is, I'll bring this v perigee and v apogee into one side and the potential energy terms to the right hand side. Okay. So now when I rearrange the terms, I get this half into v square perigee minus half into v square apogee, because half is common in both the things, right? And gm sun again, I can take them to be common, and then I get 1 by r origin minus 1 by r destination. So now what I will do, I'll substitute my equation 4 in equation 8. That is that is what I told. It's v perigee, the relation between v perigee and v apogee. This relation. So when I substitute that, uh, I get this. That is v square perigee by 2 into r square destination minus r square origin by r square destination is equal to gm r destination minus r origin by r origin by r destination. That is, I've taken the LCM on the right hand side. Now you can clearly see that I can cancel one of the r destination in the denominator. That is, and one more you can make a clever substitution is you can see that on the left hand side there is r square destination minus r square origin. So this is of the form a square minus b square. So whenever you know that a square minus b square can be given as a minus b into a plus b. So when I do so, you can see that on RHS, I have R destination minus R origin. So that will clearly simplify my RHS also. So I'll do that in equation 9. That is, I'm using this identity in equation 9. So when I do so, again, you'll get, I'll bring this 2, this a term 2 in the denominator to the RHS, and I'll get 2 GM sun by R origin in the RHS, and my LHS will be just v square perigee into R destination plus R origin by R destination, because I've cancelled one R destination, and then R destination minus R origin is cancelled on both the sides, right? So now I can rearrange the terms and bring an expression for v square perigee, right? So I'll cross multiply this, and I'll get v perigee as root 2 times gm sun into r destination by r origin into r destination plus r origin. So now I have a term for v perigee. Similarly, I have to do for v apogee. So what I will do again, I'll substitute. Initially, I had substituted v perigee equal to v apogee into r destination by r origin. So what now I'll do now is I'll substitute v apogee in terms of v perigee in this equation number 9. That is in this equation number 8 mainly. So when I do so, I'll get v apogee. So v apogee turns out to be root 2 gm sun into r origin by r destination into r destination plus r origin. So you can clearly see that for velocity at perigee, there is a factor that is depending on the destination planet's radius, right? And then again, it is dependent on its own radius too. So what I do, I'll use both the equation in the equation 1 and 2. That is, I told for equation 1 and 2 is my this equation where I have terms for v perigee and v destination, whatever I had written in first, right? So I'll substitute v perigee and v apogee in this equation. So when I do so, what I'll get is an interesting one. So I can easily get what is delta v1 and delta v2. So now I can calculate theoretically or numerically, I know what velocity I should give in order to successfully reach that orbit, right? So that is done. So now one more thing, what we have to find is, one is that what is the time taken for me to reach there, right? Even that also plays an important role when you are performing a mission. You'll have to be clear as to how much time you are taking, right? So, and also I need to say what is eccentric anomaly now. I told you what is eccentric anomaly, but how do I get it numerically or theoretically, right? So that we'll look into the next slide. So we know that from Kepler's third law, t square is proportional to r cube, given that r is an astronomical unit, right? And then the time period of satellite is t when it returns back to Earth. That is, if you look at the image here, right, the Hohmann Transfer Orbit which I had given, the time t is, let's say my satellite started from here, it reached here, and then it will again, if I don't give any impulse here, it will surely come back, right? Because this is the orbital velocity of this elliptical orbit. So when I give so, if the time taken t is for this entire orbit, that is when I return back to Earth. But our point of concern is I just want to reach here. So the time taken will be for surely half, because this is a symmetric case. So my time taken will be t by 2, right? So I can clearly say that if I have to reach apogee, the time period of my satellite will be t by 2. And then now we know that semi-major axis of the Hohmann orbit is equal to r origin plus r destination. That is, see, in this picture, this is my Hohmann orbit, right? And this is my semi-major axis. The semi-major axis is r origin plus r destination, and this is equal to 2a, right? So I can say A is equal to R origin plus R destination by 2. This is like the radius. You can assume that semi-major axis is this, right? So now I will divide it by 2, right? And then when I just, right, when I do R origin plus R destination by 2 is my radius. It is like the radius for ellipse. We call A to be like a radius, right? So this, and when I right? And then following relation can be obtained by considering the angular displacement. That is this relation. That is the t time taken is by my spacecraft to reach the apogee, and then t destination is the time taken by my destination planet. That is for the one entire period. That is, if I'm starting from here, if my planet can go through one rotation, that is 360-degree, my this displacement is just 180 minus 5, right? Because you know that my destination planet is taking 180 minus 5 angle for t. That is, for time t it is going 180 minus 5, and then we know that t destination is its uh, orbital time period. That is for the one entire thing, that it will go 360-degree. So I can divide both, right, and I can get the relation, right, because I know t destination 360 is fixed, and I just have to solve for phi, right? So when I do so, I'll get one fixed angle, right? That is called as eccentric anomaly. When I do that for Mars, if I'm doing from Earth to Mars, I get phi to be around 97-degree. That is, it means if I have to launch for from Earth to Mars, this angle should be around 97-degree roughly, right? So this is what my eccentric anomaly will help. It will clearly help me to decide, okay, let's say I'll fix this date when my eccentric anomaly is this, I'll launch my spacecraft from this orbit, right? So now let me just summarize with all the formulas that I have derived. So this is delta V1, this is delta V2, and then we have just a minute. Then we have t, that is 1 by 2 times r origin plus r destination to the power 3 by 2. Then I have a relation for eccentric anomaly, right? And also I know that whenever you're doing a computation part, always you are required to make the code dimensionless. That is, whatever constants are there, you'll have to fix it to be unity, and then you have to change the other parameters accordingly, that it doesn't affect your results mainly. This is mainly done to reduce the computation burden mainly. So when I do dimensionless, I'll just remove this g and m sun, and I'll fix it to be 1, because those are the quantities that are not varying mainly. So I can completely fix it. So only those variables, only the things which are variable, I'm mentioning in this formula. Fine. So this is the formula I'm getting. So after doing these changes, right, after making it dimensionless, our equation changed like how Popeye changes after eating spinach. So that's how easily it is for us to compute whenever it is dimensionless. So now let us go to the computation part. I hope I have given a solid, a nice talk for us to understand, okay, what happens in Hohmann transfer theoretically. So now in order to achieve, yeah, surely. Yeah. No. Actually, t by t destination is just by by ratio method. You can say that, that your planet takes for one rotation, it is t destination time. That is, destination is just a suffix to imply that it is for your destination planet. So you know that your planet takes this much time for 360-degree, and then you know that you're traversing 180 minus 5 degree in the given time t. So because you know this time t now from the previous derivation that we have done using Kepler's law, we now know the eccentric. We can find eccentric anomaly, right? I hope it clears your doubt. Yeah. So computationally, there are many algorithms which can help you solve the differential equations, right? There are many methods like RK4 method, RK2 method, or Euler method, or even Leapfrog integration, Worlet method, and many others, right? So we have mainly chosen Leapfrog integration. Why is it so? I'll explain in the upcoming slides. So mainly we know that from Newton's second law, F equal to ma, right? That is, I can say that my acceleration is, right, d2y by dt square is equal to a. This is what I know. So I can write a is equal to dv by dt, and then v equal to dy by dt, right? This is now a coupled differential equation for me, right? And now our aim is mainly to calculate, see, for a Hohmann transfer, the main one of our main concern in simulation is that we need to uh, plot, or we need to simulate how the planets are orbiting around sun. So in order to do so, we have to solve the differential equations, right? So our aim is now here to calculate the position y of t and then velocity t by solving these two coupled differential equations given here, right? So these are first order differential equation. For our simplicity, this is a really good thing that we have first order differential equation. We can do it very easily. So first of all, to do so, we have to discretize time domain. That is, if I say I have around, if let's discretizing in the sense, let's say you have, let's say you reach between point A and point B in 100 seconds. So if you have to discretize, what you will do, you will divide it into 100 time steps. That is 1 second, 2 second, 3 second, 4 second, and 5 second. And what I'll do, I'll calculate my position. And let's say if you have to reach from Delhi to Bangalore, and then it's around 2200 kilometer, and it is very difficult to say at 100 second I was here, 101 second I was here. So what you will do, you will say, okay, it will take me 36 hours to reach from Delhi to Bangalore. Let me divide it into 36 time steps. That is, you will report at every 1 hour where you are, right? And what is your velocity, what is your position, and so on, right? So that is, let's say I start at t equal to 0 from Delhi. At t equal to 1 hour, I'll be somewhere near Mathura. Then t equal to 2 hour, I'll be near Agra, and so on. And at t equal to around 36, at t equal to 36 hour, you will reach Bangalore. So this is what this discretizing time step means. So you can clearly see that let's say we are having an infinite amount of time, and what we'll do is we'll discretize it. So first one will be t naught, then t1 will be t naught plus delta t. So this delta t is just your time step as to what is the interval between your each time step mainly. So t2 will be t naught plus 2 delta t and so on, and your nth time step will be t naught plus n delta t, right? So now in order to achieve, that I can just say, that from kinematics that your position x is equal to ut plus half at square. So this is your second order approximation. But if you want to go to the third order, right, it will be 1 by 6 bt cube and so on. So we just are concerned, we are just assuming all these tends to 0, and we are just concerned about second order accuracy, fine? And in order to achieve second order accuracy, what we do is, in Leapfrog method, what we do mainly is we evaluate y at all integer times. That is at t equal to 0, t equal to 0, t equal to 1, t equal to 2, and so on. That is, I'll just say my position at t equal to t naught, then at t equal to 1, then t equal to 2, t equal to 3, t equal to 4, and so on. But I will calculate my velocity at every half interval. That is, at every 1 by 2 interval. That is like v half plus 1, then so on. That is v half, v3 by 2, v5 by 2, v7 by 2. What I will do is, I know my velocity at v half. So what I can say is, okay, my velocity at v half is this. So, and for another half second, I can just multiply with this v half, and I'll get my position y1, right? And then I'll verify with my data if this is right. Then again, I'll go with the same velocity till t3 by 2. And now I calculate what is my velocity. And now I get to know that it is v3 by 2. So till the next cycle, my velocity is constant. So this is what we do. Okay. So you can see that clearly position and the velocity are leapfrogging over each other, right? So this is the main reason why we call it as a leapfrog integration. So as I clearly said that from the equation of motion, we know that v equal to u plus at, and I can give my position y equal to y naught plus vt. And what I do is I said I calculate my position at every one integer time second. That is I equal to 1, that is y1, y2, y3, y4, y5, y6, so on. So my y, if I put I equal to 0, my y1 will be equal to y0 plus v half into delta t, right? And then my velocity will be v half will be equal to v, what was my velocity half second ago, into acceleration times delta t, right? So this is what we will put it in our coupled differential equation mainly. So now, okay, we have chosen leapfrog method. What is the advantage of leapfrog method over Rangekata, right? There are many other better schemes like Rangekata 4, or there is one scheme called as BDF2, backward differential formula. So though I not use much of this, though I'm not aware much about BDF2, but I surely know that my leapfrog is dominant over this on certain regions. Why? Mainly because we can achieve time reversibility. That is, let's say, okay, as I said, I went from Delhi, I'm going from Delhi to Bangalore. Okay, so I will calculate till when I reach Agra. Let's say I took two time steps, right, to reach Agra. One is Mathura and then one at Delhi. Let I realize, okay, I made some error, so I can come back in leapfrog method. That is, I can come back to Mathura or I can come back to Delhi and then restart. So this is one good approximation that time reversibility helps us in leapfrog method, while Rangekata or BDF4 or even Euler scheme is not helpful in this case. And secondly, leapfrog scheme, right, it conserves the energy of the dynamical system. That is, it is kept symplectic. Okay, so this is what is one of the advantage, and this strength is very crucial when we are computing in orbital dynamics. If you know, we as you clearly know that Rangekata of fourth order does not conserve energy. That means, let's say if you are orbiting, your Earth is orbiting around Sun, right? Assuming this to be Sun, if we are doing it in leapfrog scheme, throughout some infinite time, my Earth will be just revolving around Sun. But if I'm doing through Rangekata 4, what will happen is after some time, my Earth will collapse and merge with Sun. So this is not reality, right? So this is one thing that is an issue with Rangekata 4 and even with BDF4 method. So now let us look at the simulation. I'll just show you my code and we'll do some simulation here. Okay. So I'll just run my code directly. So what we have done is we have, because there are many planets involved, around 8 to 9 planets, and then we have put the parking orbits to give data every time the input as to what is the our origin, what is our destination. It's a difficult job. So we actually took help of one CS graduate who was also interested in this project, and we have made a user interface using GUI. That is, we have made the GUI using Tincter, and we have done simulations using Matplotlib only. So these are the main libraries that we have used. One is Tincter and one is Matplotlib. Initially, our plan was just to plot the orbits, but then we got to know that there is one extra library in Matplotlib which will help us to animate this. So we have used this matplotlib.animation. So and done that. So let me just run the code. So you can see the user interface is open here. So in this user interface, right, we have different planets as to what we want to plot. So now let's say you can see there is planet Mercury, Venus, Earth. Then I put a park orbit between Earth and Mars. That is, let's say I'm launching from Earth and I put it in an orbit. And when the eccentric anomaly fits in, I'll just launch it to the destination planet. So then there is Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. So let me just click, I just want to plot Earth and Mars, because I'll just say, okay, I'll go between Earth and Mars only. So I'll select my what is origin planet and what is my destination planet. So I've done that. Now I'll click on, I want to plot my Hohmann transfer orbit, and then I want to do this orbit insertion also. What will happen if we don't insert the orbit? I'll show you in the code in the upcoming things. Okay, in the upcoming a few minutes. So I'll just click on suggest simulation parameter. So this will tell me the time taken and how much time step I need to take. This we have directly inputted it put as a formula. So it will display over here. So it is just saying that it will take me around 0.77 Earth years to reach from Earth to Mars. And I'll just say my time step to one time step in 1 Earth day. Okay. So I'll just click on plot. You can see that I have plotted. So my satellite, you can just look at the interface because this is how the simulation looks. It will show the transfer time here. That is as to how much time it will take to reach there. And then the transfer distance is how much distance it has traveled. That is the distance traveled along the circumference of the ellipse. And then the elapsed time as to how much. See, mainly you can see the error arising here. So the elapsed time is what we are calculating numerically, and the transfer time is what the code is taking, how much time it is taking. You can clearly see that there is error of around 0.06 here clearly, right? So I'll just simulate here. You can see now. So when I animate it, you can see that my I'll show you again and again. So you can see that it starts from here, and the eccentric anomaly is somewhat phi, right? And then it will take an elliptical orbit, and then it will reach here, right? So you can see that the transfer status is completed. So I'll just rerun the simulation so that you'll get to know as to what's happening. So I just gave one impulse here, and then it reached here. And then what happens if I don't give one more impulse? I'll just do is I'll just remove this orbit insertion. So when I do orbit insertion, right, what happens mainly is that uh, after that your there is no delta v2 that is given. So I'll just double my time also as to for how much time I want to calculate. So when I do so, you can clearly see that it launched from here, it reached Mars, and then again it is coming back to Earth. This is mainly because there is no delta v2 that is given. So again, you can see that when it reaches again back to Earth in the Earth's orbit, right? Again, the eccentric anomaly here is not matching. So the thing is, if you fail to give one impulse here, one additional impulse here, you will not be able to reach here. And also one thing you can observe is from the exactly 180 degree from the point where you gave the first impulse, you are giving the second impulse. So this is called an ideal Hohmann transfer. So if you are giving, let's say due to some other factors, your your uh, your spacecraft reached before this 180-degree point. It reached somewhere here. So you have to give the impulse here, the delta V2. Then we call it as a type 1 Hohmann transfer orbits. Type 1 Hohmann transfer. That is when the angle is less than 180-degree. And in case you went over here and you met the destination planet somewhere here that is greater than 180-degree, then you call that as type 2 Hohmann transfer mainly. Okay. So now you can see that if I what happens if I don't do the orbit insertion, right? So, and what is the need of or what is the need of two impulse? I guess that is clear to you. So now what I'll do is park orbit to Mars. So I'll just click on suggest simulation parameter again. So I can see that I'll again reduce the time step to 1, and I just animate it. You can see that now it is not starting from Earth, right? This park orbit is just this orbit. This is not any planet revolving. You can clearly see that it is reaching Mars, right? And now what I do, I'll just double the time step to, let's say, around 2 years. Okay. So, and I'll just animate. Okay. So you can see it is launched from the park orbit. It reaches Mars exactly at the 180-degree point, and then it is going along, right? It is not coming back to Earth because we are given the second impulse. That means it is going along, right? Now what I'll do is I'll just simulate as to how it looks. I'll click on Mercury and Venus also. I'll just plot this also. And again, what I'll do is I'll launch from Earth to Mars, suggest simulation parameters. I'll again increase the time period to 2 years. Okay, 1, and then time period to 2 years. So, and then animate. So you can clearly see that, okay, Mercury and Venus is going here, and I reach from Earth to Mars, and then my spacecraft is in Mars only, right? It is orbiting Mars. And the 2 years is successfully completed, right? And now what I do is I'll just remove orbit insertion and see what happens. So when I remove orbit insertion, it reached here, and then it is again retracing its symmetric path. And again, it will keep on going in the same path, but necessarily you can see that it is not matching here. It is not meeting here. This is mainly because eccentric anomaly is not matching. So I hope the simulations helped you to understand a bit better. So coming back to the slides again. So we were successful in going to Mars now. So it was a successful Born voyage, and you clearly observed that we needed to give two impulse at two different points for an Hohmann transfer. And I hope we were successful in making this seemingly difficult concept very simple for you to understand. And it was a successful mission. Thank you all for your patience. And some of the acknowledgements we would like to give is for a paper written on astrodynamics by Professor A.E. Roy in 1977, which actually inspired us in taking up this project. I would also like to thank Dr. Mamta Dahi and Dr. Hang Ramochote for helping us in working with, or guiding us in working this on this project. And I also truly appreciate the contributions of my teammate, Mr. Manish Sharma, for who unfortunately couldn't make to this webinar. And also, a big thanks to the organizers of UG webinar series at ACS Kolkata for giving me a chance to showcase my project here. And these are the references that I've taken. And I'm open to questions. And if you need any data regarding this project, you can just visit this GitHub link. We have all the project report and our codes algorithm, and then our code, and even all the data, whatever we have taken our reference, everything is there. And you can even find our beamer presentation there. And if you want to, today I just rushed you with the derivations that we have done. If you want to know much more in detail, I've derived myself and I've uploaded the video. You can scan this QR code or you can visit this link. Thank you. Mainly, uh, uh, yeah, yeah. See, mainly Newton's laws help us in a great approximation here. That is, they are almost true here. That is one good advantage that we have got. And orbital mechanics as a whole, the thing is that the more work that we spent was in the simulation part, that is in solving these coupled differential equations. And then orbital dynamics, yes, we had to study a lot, mainly because we had to analyze as to where is Hohmann better than bi-elliptical. So that part has taken some time. There are some good books also which I have put in my reference. If people are interested, they can look in. Yeah, there are surely. Yeah, we can do it. There is, I actually didn't show the simulation, but yeah, there are, Hohmann transfer, as I said, we are doing it in idealized case, but for some planets, even type 1 and type 2 are feasible. So here, some of the code you can see, I'll just show you. In some of the transfers, right, you can see that it does not exactly meet also. So I'll just show that. These are mainly due to the computational errors that we get in the simulation. So you can see I'm doing for Earth to wait. Yes, I'll remove some planets here. So Earth to Saturn I'm doing, and I'll just click on animate. So you can see that Earth is somewhere here and Saturn is somewhere here around minus 8 astronomical units, right? And it is around, should take around 6.8 years to reach. Uh, no, that can be increased by increasing the time step. Let me just do it, no issues. So now you can see it will be a bit quick. But again, you can clearly see that this will not meet, or usually for the planets which are there in the last, right? That is, I said the cases where bi-elliptical is more favorable. Those cases you can clearly see that it does not meet. Ah, ah. So you can clearly now see that there is a bit difference. This is mainly arising due to the computational errors that we are having in the approximation in this leapfrog method. Yeah, welcome. And also thank you, Maitreya, for giving this opportunity. Yeah. Bye bye. Good night, everyone.